to the final talk. Definitely one of like the talk that I've been looking forward to, because it's a very new attack vector that was recently shown on machine learning models. So this talk will be given jointly by Professor Aydin and Dr. Seetal Potluri. So Dr. Aysu is currently an assistant professor and Bennett Fellow at the Electrical and Computer Engineering Department of NC State University, where he also leads the Hector Lab, looking at hardware cybersecurity. He got his MS from Sabancı University in Istanbul, Turkey, and his PhD from Virginia Tech. Before NC State, he was also a postdoctoral researcher at University of Texas at Austin, and his main research interests include hardware security research and cybersecurity education. Then we'll also be hearing Dr. Potluri, who received his PhD from Department of Electrical Engineering, IIT Madras in India. And after his PhD, he was also working with Xilinx for 2 years, where he contributed to the towards the automotive grade sync ICs. Currently, he is doing a postdoc at NC State University, and he also is involved in several technical program committees of the leading design, automation, and desk conferences. So, Aydin and Seetal, the floor is yours. We look forward to this talk.
Thanks very much, Shivam, for kind introduction. Are you able to hear me and see my screen?
Yes, please.
And you are also able to see this pointer as well, right?
Right.
All right. Welcome, everyone. Good morning, or good afternoon, or good evening, depending on where you are joining from. I'm really excited to be giving this talk today. And thank you for inviting us for giving this talk. So in this work, we propose a new attack vector and demonstrate its superiority over what exists compared to other attacks. The title of this talk, and this is also a paper called Stealing Neural Network Models Through the Scan Chains. It is indeed a new threat for ML hardware. So essentially what we do is we show that the scan chain attacks, which work and which is very well known and respected in cryptographic circuits, they extend towards machine learning hardware as well. This talk will be given by Seetal, by me and together with Seetal Potluri, who is a postdoctoral research fellow working with me. And just a disclaimer, so you may be seeing this red hat behind me. They are not the sponsors. It is just the skyline of Raleigh. If you are interested in this work, you can also look at our paper, which is coming up at the upcoming ICCAD conference. Here is the outline of today. I will be giving I'll be presenting the threat model and the high-level overview of this talk. And then Seetal will take it away and will deliver the real technical talk in all the glory details. And then I will come back again at the very end just to show you the results and conclude. So here is the threat model that we have. The bottom line is we don't invent a new threat model, or we don't have any unique assumptions in this work, any unique things. Instead, what we do is we combine what existed before in scan chain attacks and model extraction attacks. So model extraction attacks, they try to steal valuable machine learning models because these models are very costly. It may cost up to $10 million these days due to the value in data and the complexities in the training process. We assume that the training phase is trusted. So these models are developed in secure cloud applications and so on. And then the model is deployed to an edge device. And then the model is used for inference to doing certain classification or regression tasks. The adversary may have physical access to these devices, and the adversary can send inputs, look at the output responses, and the adversary tries to reverse engineer this design and extract these machine learning models. That is the attack called model extraction attacks. Scan chain attacks assume that, so there is a scan chain interface, which is very useful to test circuits. And in the scan chain attack model, the adversary has access to these scan chains. The adversary can either be a capable end user, or they can be the outsourced assembly or test service. And then the adversary can look at the responses of these scan chains and tries to reveal the threat, tries to learn some values. This is very well known in crypto circuits. We assume that this also can be done on machine learning hardware accelerators. And as I said, the one assumption is that the adversary has access to these unlocked scan chains. What we show is that you don't need access at a very fine granularity, as in crypto. We can just have an access to these nonlinear output units, and that the attack still works with some mathematical analysis. So that is our threat model at a high level. And here is the outline of this talk. The attacker will target a circuit just like what I've shown here. This is a realistic assumption because similar circuits with similar scan chains has been used in the industry and in the academia. For example, the IRIS paper is built on this model. The adversary has access to this scan chain output of the activation results, but not to these partial results, these weights, the fully connected neural networks. The adversary can only access to this activation output, the nonlinear, for example, the rectified linear units output. So the adversary will first apply some inputs and observe these nonlinear responses. What is critical here is to selectively activate or deactivate certain targeted neurons, which is rather non-trivial to establish. To do that, we will be inspired from analog circuits, and we will do what is called the small signal analysis to extract these weights. So weights and biases are the key critical parameters that we are trying to extract. Then we will Seetal will be identifying a particular issue that happens when you have a negative weight and a negative bias that requires some special treatments. And then we will be constructing this whole problem of model extraction, weight and biases extraction, as a linear constraint satisfaction problem, and apply certain relaxations therein to have an efficient attack. And finally, we will be talking about how to generalize these, not just to first node or the first layer, but to n nodes and m layers within these nodes. And we will present an automation script that can do all this analysis automatically, independent of the neural network size. So that is the outline of the attack. Now I will be giving up, I will be stopping the sharing, and Seetal, please share your screen, and then we'll take it from here.
Right. So am I audible?
Yes.
Oh, that's nice. I hope you're able to see my screen, Aydin.
Yes.
Okay, that's nice. So this is where I will continue from. So this, thanks, Aydin. first for providing a very nice introduction to the paper. And this slide actually provides a glossary of different symbols that we use in this work. And this paper is more of a mathematical treatment of the subject. So that is why we're including all the symbols up front, because we will be using a lot of these things later in the upcoming slides. This will help actually to prevent any abuse of notation. Now, let me use laser. Right. So this paper focuses on scan chain based model stealing for hardware implementation of fully connected neural networks. So the figure on the left top corner actually shows two consecutive layers in a fully connected neural network. We assume that ni minus 1 is the number of neurons in the I minus 1 layer, and ni are the number of neurons in layer I. And each node that you see here in this figure is a neuron or a perceptron that is basically a linear weighted summation of the input features plus a bias after activation. So the weights together with the bias actually constitutes the model parameter set for the neuron. And the choice of activation function. So basically, if you look at this representation, it shows the way the neuron is constructed. Essentially, it's a linear weighted summation of weights plus bias, plus there is an activation function. So this activation function is chosen to be a rectified linear unit, which is ReLU, as popularly known. And essentially, if you look at this diagram, we show that the output of layer I is xi plus 1, and the input to layer I is xi, which has different components. And wi that you see here is the weight matrix for layer I, which consists of each row in this matrix is essentially the model weights for one neuron, and all the rows together forms the weight matrix for the layer. And then you have a column vector bias for the layer, where each unit actually represents the bias of the neuron, and H is the ReLU, right? So essentially, this is a fully connected ReLU network, and because we use a ReLU activation function, the output of every neuron in this network is a positive number. And we consider a double precision floating point representation. So if you look at the input to the first layer neurons, it could be positive or negative. So it's a double precision floating point number that could be positive or negative. But if you look at the input to all the remaining layer neurons, that is all layers other than the first layer, then because of the ReLU property, all the inputs to the remaining layer neurons is a non-negative number. So this slide actually describes the key concept that we use in this paper. As Aydin described, we borrow the concept of quiescent operating points and small signal analysis that is used from in analog circuits model extraction to neural network model stealing. So we have a notation here. In the old slide, we have seen that xi is the input to the ith layer. So because the layer indices begin with 0, x0 is the input to the neural network, and it consists of many entries. Suppose we assume that all the entries in this input vector is 0 except one entry, which is the first entry, which is the non-zero entry. And we denote that entry as C0, where 0 is the 0 index for the entry in the input vector. Then suppose we are trying to observe, by applying this input to the neural network, we are trying to observe the output of first neuron in the first layer. So let FC be the output of layer 0, neuron 0. And consider these are the values of the weights. Now, the first neuron in the first layer has many weights. So the superscript talks about the layer, and the first index talks about the neuron index, and the second one talks about the weight index within the neuron. So we are talking about two different weights within a neuron. We have not shown the other weights for simplicity, and this is the neuron bias. Suppose if I apply inputs and try to sweep the value C0 and try to plot f of C0 as a function of C0, this is what we observe in simulation. So this is the plot when I'm trying to put all the entries 0 except the first entry, right? This is the plot. And the same plot When you make all entries 0 except the 7th entry, which means you're trying to attack the 7th weight, this is how you get it. So because the first weight is positive, you get a plot like this. And because the second weight is negative, you get a plot like this. In both cases, we are trying to find an operating point which is stable in the linear region of operation, because in analog circuits, we try to expose the gain and transconductance by actually placing the transistors in the linear region of operation and then doing small signal analysis. In the same way, here we are trying to place the selected neuron in the linear region of operation. And why we are choosing the operating point very deep within the linear region is because when you're trying to apply a perturbation around the Q point, the neurons should remain in the linear region of operation. So in order to do that, you need to place it quite deep into the linear region. So this is the concept of a Q point. And then now we have seen how to extract a model parameter by placing it in the linear region of operation, right? So there are different possibilities of weights. So given a neuron and given a weight that you're targeting, and the neuron also has a bias. So there are 4 possibilities. The 4 cases are that the weight is positive, the bias is positive. And another case is that the weight is positive, but the bias is negative. And the weight could be negative and the bias positive. And the last case is that both are negative. Now, if you look at the point carefully, it's actually possible to get an independent Q point for each individual weight for cases 1, 2, 3, except case 4. It is because of the non-negative input property that we have discussed before. So all the deeper layer neurons will only receive a non-negative input. So if you have a weight that is negative multiplied by a non-negative input, then the whole thing will be negative plus negative bias. Then the sum of all this will always be negative, and when you apply a ReLU activation, it becomes 0. So it is the neuron always remains in the 0 region. So it is not actually possible to expose the model parameter, which is not the case with the first 3 cases. In the first 3 cases, you can actually make the neuron output positive and make it in the linear region and get a Q point. So this is a challenge which we shall see at a later point in time. So in order to address this challenge, we use something called a common Q point analysis. So 2 slides back, we have seen what is the definition of a Q point and how to place a neuron in the linear region of operation in order to attack the weight. But when you have a case when the weight as well as the bias together are negative, then we have shown that it is actually not possible to extract the weight. So in order to address this challenge, we propose something called a common Q point analysis, where we try to have more than one non-zero entry in the input vector. So in the earlier case, we have seen either C0 is non-zero or C6 is non-zero. But here we have more than one entry which is non-zero. And in this case, let f of C0, C1 be the output of the first neuron in the first layer. And in this case, unlike the previous case where the output of the neuron is a linear function of the sweep parameter, here because we have 2 sweep parameters, the output is actually a surface, and the linear region, unlike the previous case, which was a straight line, it's a plane here. So essentially, in this particular diagram that you see, we are considering only 2 parameters. So it's a hyperplane in 3-dimensional space. But when you're considering a common Q point for n different model parameters, then you have a hyperplane in n+1 dimensional space. So this concept we will use later when we try to attack the deeper layers. So even before proceeding to that, we will try to show examples of how to attack the first layer. So even before that, so we have shown how to find a Q point. So now let's understand how to apply small signal analysis. So small signal analysis is very popular, and it's used by analog design engineers to extract the model parameters of an analog integrated circuit. So in circuit design, so we have a transistor network similar to the connections of neurons to form a neural network, right? So there, if you consider an amplifier, for example, people are interested to find the transconductance and the gain of an amplifier. So they consider the different configurations of the transistors and try to place each transistor in a particular region of operation in the linear region, and then apply certain voltages at the gates of different transistors and try to drive different transistors into different regions of operation and then calculate the gain and transconductance. In the same way, we try to use a small signal analysis after finding the Q point in order to extract the model parameters for neural networks. So as a simple example, if you look at a single transistor, and if you are interested to find the gain and transconductance, you have 3 different inputs that you can apply: the source, gate, and drain. And then you can place the transistor in the linear region and then actually apply small signal analysis to find out the model parameters by observing the outputs. So we borrow this concept from analog circuits and apply it to neural networks. Now, in the context of small signal analysis as applied to neural networks, what we do is that we query the neural network and find out something called a Q point. In the previous slide, we have shown that we have a parameter called a sweep parameter. So we sweep this parameter in order to find the Q point by making query to the neural network multiple times. And once you find the Q point, if you denote it as x0, as we have seen before, and then you make a small input perturbation, delta, which is less than a capital delta, which is the amplitude of perturbation around the Q point x0, and let's call it x0p. And then for both x0 and x0p, suppose you are looking at attacking a particular layer, say layer 2, then you need to run the classifier all the way from the first layer to layer 2, and then interrupt the classification, and then capture the outputs of the neurons of interest in the second layer, and then use calculus on the extracted outputs of the second layer in order to extract the model parameters. So if you look at the diagram below, what we can see is that there are interspersed phases. The first phase is the classification phase, where we actually try to run the chip in the classification mode. That's why you have a fast clock, and then you have a gray region where you do a clock gating, so nothing is done. Then you have a scan out phase where you dump out the data of the particular layer, as I didn't mention, the coarse-grained scan chain axis, and then you have another clock gate. So this entire thing is called one query, and then you continue, right? So in order to do the dump, you actually need to place the chip in the debug mode. So every chip actually has a J tag. So using J tag, you can do a signaling of TMS and put the chip in the debug mode, and then you change the scan enable from 0 to 1 in order to dump out the scan data. So let's see with a small example how to do this. Suppose you have x00. The 0 is the index of the parameter that you're trying to attack. Suppose you're looking at the first parameter, then all other entries are non-zero, and only the first entry is, all other entries are 0, and only the first entry is non-zero. And let C op with the operating point or the Q point, and delta 0 with the corresponding small signal. Then let f of x0, and this index 0 actually corresponds to the index with the neuron 0 output, oracle response corresponding to the Q point, and then the f of xp0 is the oracle response corresponding to the perturbation. Now we have seen this formula before. It actually computes the layer output given a layer input and the weight matrix plus bias vector along with an activation. Suppose if we use those values and compute the black box response of both the Q point as well as the perturbation, this is what we get. And because C op is the Q point, ReLU disappears and only the term inside remains. So if we subtract these two, what we get is basically delta naught into the weight. And then if you divide, you get actually the value of the weight. So you just have to make the queries to the neural network using the Q point as well as the perturbation, and then divide by the small signal, then you get the weight. And then if you substitute it back in this equation, then you can actually find the value of the bias as well. So what we have done basically is to run the classifier, interrupt the classifier, dump out the scan data, and then using those values on the small signal, actually retrieve the value of model parameter weight and as well as the bias. So this is a very simple example where we have done only for the first model parameter of the first neuron in the first layer. Now you can generalize this to all parameters for the first neuron in the first layer by actually changing the index here. So here it was 0 before, now you can make it k and then run the same attack. And if you see here, earlier it was delta 0 and here we have delta k. So the perturbation also changes depending on the index. And the same thing can be extended to the bias. So once you find the weight, you can actually substitute it back actually to get the bias. So earlier we found the same thing without the parameterizing. Now we are parameterizing using a parameter k. Now this can also be further extended to all neurons in the first layer by parameterizing m. Here we have 0, but here we have m here, and then you substitute m here, and here as well. So you find the weight, and then you retrieve the bias. Now, what we have seen before is a way to actually find out model parameters for all neurons in the first layer using scan chains. Now, it is also possible to attack layers beyond layer 1, but there are some challenges. The challenges are that in the first layer, all the entries in the input and the filter have a 1-to-1 mapping. So you can actually put the 0 entries for model parameters you're not interested, and then just expose the weights as we have seen. You don't have the common Q point problem in the first layer because you're allowed to enter the negative values, right? But if you're looking at deeper layers, you have a problem because the small signal of any given index in the first layer is broadcasted to all inputs to the second layer, because so basically every neuron in the second layer gets inputs from all the neurons in the first layer. So if you have a small signal, the small signal will be broadcasted to all inputs, all neurons in the first layer. So outputs of all neurons will contain the small signal. So every model parameter in the second layer neuron will get the same small signal. So essentially, if you consider k is equal to 0, then if you are looking at a particular neuron, then what we can see is that every neuron, so basically this shows the first neuron in the first layer. It is a function of delta naught. And similarly, if you change 0 to m here, what we can see is that every neuron output in the first layer is also a function of delta naught. So all neuron outputs are functions of delta naught. So each neuron in second layer 1 is layer 2, second layer, it will receive all these things broadcasted to each model parameter. As a result of this, we don't have we are unable to expose weights just like layer 0. And also, in spite of that, we are facing a problem of undetermined system of linear equations, because of this small signal being broadcast, we get exactly one equations, but we are supposed to solve so many n naught unknowns, right? So this is a challenge. So what is the challenge we are facing? We have an underdetermined system of equations, which means we have only one equation, but we are trying to solve for n naught unknowns. How to solve this? So in order to solve this system of underdetermined system of linear equations, so we are actually using a concept called localization, where if we are looking at a particular weight under attack for a neuron in the second layer, if you call it WUA, then you need to find a Q point to apply at the input of the neural network that activates exactly k plus 1th neuron and does not activate the remaining neurons in layer 0. And any perturbation to any arbitrary location to the input. And then you observe the corresponding neuron in layer 1, and then you just retrieve the weight, because you are activating exactly one neuron in the prior layer. So naturally, you don't have the broadcast anymore, because all the remaining neurons output will be 0 because of the relay activation. So using this, we are able to actually solve the challenge of underdetermined system of equations, because now we have exactly one equation and you're solving for one unknown. But this is the way to do it, but we have not yet solved it. So how to solve this is by using a system of constraints, because we are trying to activate exactly one neuron in the prior layer corresponding to the weight under attack and not activate the remaining neurons. So we need to actually formulate it as a system of constraints and use a constraint solver to find the Q point. So because the neuron function itself is linear after activation, so we can actually formulate it as a set of linear constraints, both the activation neuron as well as the deactivation neurons. So essentially, this translates to the constraint satisfaction problem being a linear constraint satisfaction, LCS. And if you look at the weight under attack index, then we formulate such that it is actually greater than -1 into bias plus a target eta, where eta is a very high positive value. Because what we have seen when we ran the constraint solver is that it sometimes returns a Q point that is exactly on the border. That means it says it's greater than 0, but it is like 0.00001. But then when you apply a negative small signal, it actually goes to the 0 region, which is not good. In the same way, because we are trying to deactivate all the remaining neurons in the prior layer, we need to add another constant alpha, which is a very small negative, which is a significantly small negative value, so that the neurons that are supposed to be deactivated are always deactivated and are not on the border between activation and deactivation. So we have seen this issue. Because when we actually make eta 0 and alpha 0, we have observed a very significant model extraction errors. But when we ensured a very high value of eta and alpha and a negative value of alpha, then we have seen very good accuracy. So we have talked about case 4, where we have a negative weight and negative bias. So this comes into picture here. So when you're looking at deeper layers, right? So all the inputs are positive. So naturally, when you have a negative weight and bias, it is actually not possible to attack this, because even if you do an LCS and find a neuron which is activated and all the remaining neurons which are deactivated, but this parameter, since it's negative, you can never extract it. In order to solve this, we need to find a common Q point as discussed before. So the formulation remains the same for this and this, except that we add a new constraint here, which is the additional constraint, which is about a first positive weight. So when you start attacking the weights, you'll get some positive weights also, right? So if you have a negative weight, then you just neglect it, and then you go forward to find the first positive weight and then iterate over the negative weights later. So when you find the first positive weight, you need to couple this weight along with the other weight under attack in order to find a common Q point. And then around the common Q point, we need to do the model extraction. Right. So we have seen how to extract for the second layer and the first layer. Now, if it is actually possible to attack any layer using this technique by selectively activating and deactivating the neurons in the prior layer. So the way we do it is an iterative way to extract model parameters of each layer. So once you attack layer 1 and then you attack layer 2, and once you attack layer 2, then you extend to layer 3 and so on. So this is the algorithm used to actually automate to extract large fully connected networks of arbitrary depths and sizes. So the algorithm accepts the model to the previous layer, theta I minus 1 cap. We use a cap here because it's an approximated model which you're trying to extract. Theta is the original model which you don't have. And delta is the small signal. Eta is the target for the selected neuron. Kappa and nu are the, the range. By the way, I forgot to explain the significance on eta and kappa. Earlier, we just used a single variable kappa. When you do that, what happens is that sometimes the value of tau, it is choosing some negative value and it is going into the deactivation region. So you need to choose a value of nu, which is positive, and then a value of kappa, which is significantly lower than eta, so that the value of the positive weight significantly dominates the value of the negative weight. Because why are we using a common Q point? It's because the negative weight is actually ensuring the neuron is in the zero region. So if you want to ensure the neuron gets to the positive region by including a positive weight, then you need to have a very high eta as compared to kappa. So that is how we choose nu, eta, and kappa. And then we are here. So we iteratively extract all model parameters. The first case is when you do a Q point search and then do small signal analysis for cases 1, 2, 3, where you have no problem at all. And then you have the case 4, where you have a negative weight and bias scenario. There you use coupled constraints, as we have discussed in the last slide, in order to extract the model parameters by finding a Q point search and SSA. Even in these cases, we have found cases where sometimes the solver just hangs up and says, I cannot solve. In those cases, we try to relax constraints for already solved weights. And then we substitute back those weights by doing an oracle response using incremental extraction. And in this way, we keep continuing until we get the model parameters and biases for all neurons in all layers. So here, I'm going to stop and let Aydin continue with the talk.
Thank you very much.
Thanks very much, Seetal. So how much time do we have?
For Q&A?
I think we have a good 5 minutes, I think, if you want to wrap up, and then a couple of minutes for Q&A.
All right, I'll definitely do that. Oops. So I will just conclude on this attack results. Then, sorry about this. Okay, so this may look like a complicated table, but let me walk you through it. So we do not, again, generate this table. We are just copying it from an earlier publication from Crypto 2020 that was proposing a cryptanalytic attack on black box machine learning models. What they show is they show this attack on different architectures. So this column shows the hyperparameters of the machine learning models. For example, in this case, the input layer has 784 nodes. There is only one hidden layer that consists of 32 nodes, and the output layer only has one node, which constitutes to about 25,000 parameters to be extracted. And their paper showed, so 28 is the crypto and 27 is an ICML paper, I believe. They show the number of queries number of inputs needed to extract these many parameters and the maximum error that they have for extracting, so between the extracted weight and the real weight. The bold fonts here show the results of our attack, which quantifies the superiority that we can do this attack with fewer queries, significantly fewer queries, and our error rate is actually the numerical error, right? So this just depends on whatever precision you use in your floating point library. This is not just true for one architecture, but for any given architecture, our queries is lower and our error rate as well is lower. And moreover, we don't show this here, but our attack, so their attack, the cryptanalytic attack, is limited to certain nodes and certain depths, whereas our attack can scale much better and can attack even more complicated neural networks. This is, of course, is possible by observing these intermediate results through the scan chain. So yeah, that's just shows our results. And to conclude, the scan chains are extremely useful for testing your chips. That is why we use scan chains. But at the same time, this shows this can reveal a vulnerability, not just for crypto, but also in the context of machine learning hardware. And that scan chain attacks don't require fine-grained access as in crypto. You can just leak out the intermediate layers information and use that with some mathematical analysis, as Seetal described, to come up with a very practical attack, and that can outperform black box cryptanalysis. We show some interesting ideas that we derived from analog circuit design and small signal analysis to extract these weights. Attacking deeper layer is difficult, but this can still be done and it can be automated by what we have shown. And the results are much better. Our future work is to extend this to convolutional neural networks, which, by the way, to this date cannot be attacked with cryptanalytic black box techniques. So we may be interested in doing this CNN attacks using the scan chains. So that will conclude my talk. Thank you very much for inviting us to give this talk. And if you are interested in this project, or there are some others as well, please shoot me an email. There are always some opportunities for talented PhD students. And thank you very much.
Thank you, Aydin and Seetal. That was a very nice talk. I will maybe start with a quick question on so the extraction that you're aiming here. So currently it is based on fully connected layers, and is it an exact extraction? Basically, that means like the full architecture and all the weights can be recovered, or like I think that there is a taxonomy where they say high fidelity extraction or a task equivalent accuracy extraction or something.
Right. So high accuracy extraction talks about the functional accuracy of the model after you extract, but high fidelity talks about the error in terms of each weight. So what you'll see here on the last column is the max of the, so if you have n number of model parameters, the max of the errors in the extraction in all of them. So it's a conservative case. So you see that the error is really small, which means that all the parameters are successfully extracted. And the worst case was 2 power minus 54, which, as Aydin mentioned, is the double precision floating point error for is the limit, right? That's the best that you can get on a double precision floating point. Probably if you can do a long int with 128 bits, probably we'll get a 0 error because the weights are actually double precision floating point.
Any other questions?
I have a few questions. First of all, did you check it on real systems or only on simulation?
Yeah, so checking on a real system is difficult because at the customer end, companies disable scan chains. So that's why I didn't mention ahead in the threat model that this threat is actually a threat at the outsourced testing. So there are multi-billion-dollar companies which do outsourced testing. So if a company actually sends their chip along with the model for functional testing at an outsourced testing unit, then this kind of threat actually is available there, not really at the customer end because JTAG is disabled. So we have even talking to Rescuer. So it's not actually possible to get a device with JTAG enabled.
Okay, maybe we'll touch bases later on.
Right.
On this topic, this is very. We are very interested in that aspect. I have other question. First of all, can you do the same for if you are not using Relo but other activation function?
That's actually a good question. So the entire idea beginning from the whole thing is based on the ReLU activation function. But I think it is possible to extend to other activation functions also because the concept of small signal analysis in analog circuits is basically to put into the linear region of operation in case other activation functions also show some kind of a linear region and a nonlinear region. If you do a Taylor series expansion of the activation, then it's definitely possible to extend this technique to that. And the idea is to basically push neurons into the linear region and then extract using small signal analysis.
Okay. Last question, you're using a floating point and in many systems, particular for a low power, we are using a quantizational binarization. How it will change your result? It will be easier or more difficult to get the result under these conditions?
It's actually a very good question. So because we are looking at a constraint satisfaction problem, in our case, the constraints were linear. But if you constrain the values to be more discrete of like an integer or a little more reduced precision, I think the problem becomes more hard because linear programming is polynomial time, but integer linear programming is NP hard, right? So those challenges will come into picture when you quantize more and more.
Okay. Thank you.
There's a question from the audience. So will this technique work with a compactor and also if you're using multiple chains?
Oh, I see. So in our threat model, we are assuming EDT bypass mode. So we do not consider the compactor. Including the compactor would be an open problem. It's a different problem. So we are bypassing the compactor in our work. So definitely it becomes more complicated when you use a compactor because of the nonlinearity introduced by the compactor. What was the second part of the question?
Like if what happens if you're using multiple chains?
I think it's okay to use multiple chains because you can get the information from all the chains anyway, whether it's a single chain or multiple chains. As long as you do an ETT bypass, you can get all the chains. So no problem.
Thanks, Seetal. I actually have a very generic question more on the model. So like on the threat model, I think it is very relevant because in most of the cases, this machine learning will be an IP and it will be integrated into some other chip who will control the scan chain, and that IP theft is a major threat. But in many cases, like the machine learning architecture would be there, but weights and all will be programmed into a memory,
right?
Which might be later installed or let's say programmed after the testing or the activation phase when the scan chain is disabled. So in that case, so we'll be limited only to the architecture or like how?
Right. So I think I understand your question. So yeah, so in testing there are different types of testing. So typically what is done before is something called structural testing, where you test for stuck faults or timing faults and so on. But recently the popularity of system level test has grown up so much that companies are actually outsourcing even the system level test to the foundries and outsource testing units. So when you look at a system level test, you need to actually put the model and then send the system to the unit for testing. So then only they can actually test whether your classifier is working within the levels of your accuracy and labeling is correct and all that, right? So that's what we say in our threat model in the paper.
Okay. Thanks again for this wonderful talk, and also making this effort to actually coming this early in the morning to actually present. So with that,